Welcome back to 1-2 notes this time. As of September 9th, you should be able to pick up your workbook for Algebra 2. So this is page 10 in your workbook. If you do not have your workbook yet, no worries. I've actually made a little bit of changes to this one. So you can just follow along on your own notes. So this time we are talking about translation. So imagine picking this shape up on a graph. So say this blue one. If you could pick that up off the graph and move it, you agree that you can move it left, right, up, or down. You could even combine some of those where you move it like left and down. You could flip it. We're going to look at a fancier word called reflection. So there are different things that you can do with it. So this one actually talks about how does it affect the intercept. So the answer there is, in the first example, your graph just moved down 3. So it moved your y-intercept down 3. You went from having one x-intercept to 2 x-intercepts. Some other vocabulary that I want to make sure that you know that you will see in this section work is called a vertex. The vertex is just the bottom point there, the point of change. It could also be the top point if it looked like that. So in this case, the vertex of the blue graph, let's call the blue graph f of x. So vertex of f of x is 0, 0, because it starts right there, dead center, 0, 0. The vertex of, let's call this one g of x, that just gives them a name. That way we're not saying the blue one and the red one. That's not really mathematically correct. So we name them f of x or g of x. Not something you would necessarily name your kid, but the same idea. G of x is at 0, -3. So notice the entire graph moved down 3, and the only thing that changed for the vertex was that it also went down 3. So in this example, the other vocabulary word we're going to look at is something called axis of symmetry. Remember in art class, symmetry is when one side is symmetrical or the same as the other. If you were to fold it in half at that point, they would touch each other. So like if it were wet paint, it would just be wet paint on top of each other. When we write the axis of symmetry, we always say x equals. So for f of x and g of x, it doesn't matter where it is, we're going to say it's x equals, because that is how we write a vertical line. You may remember that from Algebra 1, you may not. It's okay, you're learning it now. And both of these have the same axis of symmetry. It's at 0. Notice that that's your x value. That's no coincidence. So if I look at this example, let's again name the blue one f of x because it's the exact same one as the one above. And instead of g of x, let's use h of x. Just kidding. They've already named this one for us. It is g. So we have another g. Okay. So vertex for f of x, we have already said is 0, 0. That didn't change. Forgot to put f of x there. So for g of x now is at 3, 0. So notice that the 3 is on the inside and it has a negative attached to it, but it was really positive. It went right. For axis, whoops, helps if I could spell correctly. Axis of symmetry. Remember we put x equals for both. This one is at x equals 0. And this one happens to go through x equals 3. Notice those are the same x values as our vertex. Okay, let's look what happens when something reflects. So to reflect means across the x-axis means that something this shape, when it reflects, would then be going down. That's a bad drawing because it should be the exact same. So like the same width and whatnot, just going down. That's the x-axis. Okay. The y-axis would be, instead of this way, it would be this way. But funny things happen. If I pick that up and flip it, so maybe a two-toned parabola would help. So we got the pink and the purple. So if I pick up that pink and purple and flip them, other than the colors changing, it's still the exact same. So depending on what it looks like, reflection across the y-axis may change or it may not. It just depends. So what does it look like for the equation? So to reflect across the x-axis, here's the important part to write down. It's a negative in front of entire equation. So if something is asking to reflect across the x-axis, my equation is x squared minus 2, and I put a negative out front. Then I remember my distributive property and get negative x squared, and then the tricky one, negative times negative is positive 2. So there is the reflection across the x-axis. For the y-axis, the negative is grouped with the x. So what does that look like in this example? So where x was, it's now got a negative joining it. And so this is what it looks like. Envision wants you to work your brain a little harder and think about negative x squared. This negative x times negative x, which is positive x squared. Okay, so let's look at what those look like on Desmos, and we are finished with this example. So on Desmos, I actually already have all 3 of these graphs. Let me turn everything off. Okay, so here was the original. Then it asked for reflection across the x-axis. So imagine reflecting it across the horizontal line there. So I would show you, but there's no pointer on there. This is what it looks like. Yep, sure enough, that is correct. If I were to fold across the x-axis, the green and the purple would touch. Then notice I did the unsimplified version of our y-axis, and it is the same, because if I flip that across the vertical line, it is the same. Okay, so try your one problem and then on to the next video. All right, looking at vertical stretches and compresses or compressions. I did write some little information here on the left-hand side, good notes to have. What we're talking about is if I have a normal shape, let's say an absolute value. So the V is 45-degree angles both ways. I could stretch it so that it's wider or compress it so that it is skinnier. Still an absolute value with different slopes. If you think back to Algebra 1 about how steep something is. So vertical stretch and compress. In this particular example, you are looking at when x is -4, what is y? So here's your normal time. Just the y equals absolute value of x is the example I use just to kind of get my mind right. And this one is y equals 1, or the absolute value of 1/2 x. So if I plug this in, to Desmos or whatever, I will see that my new y values are 2, 1, 0, 1, and 2. Notice that means my y values went down by half. If I graphed it, I also notice here's absolute value of x, absolute value of 1/2 x. Looks, those colors aren't a whole lot different, but they look more like that. So the stretches and compresses just help say that it is getting wider or skinnier. All right, next up is example 4. What happens when we do combinations of things? So when I have a minus sign on the outside, that means to go down. Okay, so maybe over here we take a little note, a little side trip note. Where we write that if there's a plus sign on the inside, it means to go left. If there's a minus sign, it means to go right. So that's opposite than what you think, like what you normally think for yourself, because negative on a number line is left, but it's the opposite here for the inside. However, on the outside, plus means up, and minus means down. So if we take those in consideration and we see that this minus 4 is on the outside, that means that I'm going down 4. So if I have this picture here, I want to know where these points are. So step 1, I'm going to label all of these. This looks to be -4, 2. -2, and then 1, 2, 3, 4. -1, 1, 2, 3, and 1, 7, it looks like. So if I want to move this graph so that it goes down 4, then if I go down 4 for this one, 1, 2, 3, 4, I'm right here. If I go down 4 here, I go 1, 2, 3, 4, down 4, 1, 2, 3, 4, 1, 2, 3, 4. Notice I have the same shape as before. And that's all that this question's asking. Using the graph, we're going to graph the function when it goes down 4. What about this one? Using our rules, I'm going to zoom out a little bit, means we're going to go right 3 and down 2. So this one's going to go right 1, 2, 3, and then down 2 puts me right here. Right 3, 1, 2, 3, down 2. 1, 2, 3, down 2. 1, 2, 3, down 2. I'm underneath there. Notice it's the same shape, just moved over to the right 3 and down 2. Pretty simple, but it looked more complicated than it actually was. All right, final video for the 1-2 notes. If you hear anything in the background, I'm sorry. They're grinding up somebody's brush and trees that they cut down. So I'll try to make this quick so that that doesn't get in the way. Number 5 says, what transformations of the graph f of x equals absolute value of x are applied to the graph to graph the function g? So what things did I need to do in order to graph the function g? So if you remember, up in our last example, a plus sign on the inside meant to go left. So those are the easiest ones. So left 3. And then if I have a number on the very outside, that is a vertical. And then stretch. So a vertical stretch happens when the number out front, so we'll call it A, is greater than 1. And the positive or negative does not matter. So if you want the proper usage there, we're going to say the absolute value of A is greater than 1. So it could be -2, it could be -3, it could be 3. And what that means is it's going to make the graph skinny. But notice this is a fraction. When it is a fraction, it is called compression. And that's when it is between 0 and 1. So again, it could be negative. So like -1/2 is still a vertical compression. The difference is that the negative would make it reflect. And in this case, it does not. So vertical compression of 1/2. So that's all at once. You will see this type of question in every unit all year. So when it says what transformations, it's asking, did it go left, right, up, down, reflect, so forth. Okay. What if you're given the graph and you got to write the equation? Okay, that's taking it up a step. Okay, but you can do it. First, you need to decide, is the picture absolute value or quadratic? There are other types of graphs, if I could talk, sorry, that exist. But for this section, it's either absolute value or quadratic. We're not trying to throw too much at you just yet. Remember, a quadratic is a parabola. Absolute value is the V shape. So this one must be absolute value. So that means that I am going to use this one. All right. To determine what A is, I look at the slope. Over 1, down 1, over 1, down 1, over 1, down 1. So that's just 1. However, it's not going in an up direction. So remember over here, my picture that I drew on top of is an up position. It is down. That means A is -1. All right. My vertex is H and K. So minus -2 and then -4. All we have to do is clean it up. Envision is not going to want you to put 1 there, although it's acceptable in my book. But if you want it counted correct on Envision, they're just going to have a negative out front, no 1. Then, if you recall from when you learned negative numbers, maybe 6th grade, 5th grade, I'm not sure, minus a negative is positive. And then down 4. Here's a way you can check your answer. Type it in here. So negative, whoops, not 2 of them. Absolute value of X plus 4 minus 2. Is that the same picture as your notes? No, because I typed it in wrong. It should be plus 2 minus 4. So let me change those numbers. Sorry, that's what I get for trying to do it from memory. There we go. Now, is it the same picture as our notes? Yes, so I did it correctly.